Picture this. Right now, as you're watching this video, an object from another star system is racing through our solar neighborhood at over 100,000 miles per hour. It's been traveling through the dark void between stars for potentially millions of years, carrying with it secrets about alien solar systems, the formation of planets, and the very nature of our cosmic neighborhood. This isn't science fiction. This isn't speculation. This is 3I Atlas, officially designated C 2025-N1, the third confirmed interstellar object ever detected passing through our solar system, and it's unlike anything we've ever seen before. What makes 3I Atlas so extraordinary? Why are astronomers around the world scrambling to observe it before it disappears forever into the depths of space? And what does its discovery tell us about the countless other interstellar visitors that might be silently passing through our cosmic backyard without us even knowing? By the end of this video, you'll understand why 3I Atlas represents one of the most significant astronomical discoveries of the decade. You'll learn about the bizarre characteristics that make it fundamentally different from any comet or asteroid born in our solar system. And you'll discover what this mysterious visitor might teach us about the alien worlds it came from. Worlds we may never be able to visit, but which are now, in a sense, visiting us. But here's what should absolutely blow your mind. 3I Atlas is just the beginning. Based on what we've learned from this object and its two interstellar predecessors, scientists now estimate that there could be thousands, perhaps even tens of thousands, of interstellar objects passing through our solar system at any given time. Most are too small or too dark for us to detect. But they're out there, silent messengers from distant star systems, each one carrying information about worlds beyond our reach. So buckle up, because we're about to take a deep dive into one of the most mind-bending discoveries in modern astronomy. We're going to explore what makes interstellar objects so special, examine the real scientific mysteries surrounding 3I Atlas, and then venture into some fascinating what-if scenarios that will make you question everything you thought you knew about our place in the cosmos. If you're ready to have your mind blown by real science and tantalizing possibilities, hit that like button and subscribe, because we're about to journey beyond the boundaries of our solar system without ever leaving home. What makes something interstellar? Let's start with the basics, because understanding what makes an object interstellar is crucial to appreciating just how remarkable 3I Atlas truly is. Our solar system is home to trillions of objects. Planets, moons, asteroids, comets, and countless chunks of rock and ice. Every single one of these objects is gravitationally bound to our sun. They orbit in predictable paths, following the same cosmic choreography they've performed for billions of years. But interstellar objects are different. These are wanderers, cosmic nomads that were born around other stars, in other solar systems, and somehow escaped their home systems to drift through the galaxy. When we detect them, they're not orbiting our sun. They're passing through like a stranger walking through your neighborhood on their way to somewhere else. The key signature of an interstellar object is its orbital trajectory. When astronomers calculate an object's orbit, they determine something called orbital eccentricity. Objects orbiting the Sun have eccentricities less than 1, but interstellar objects have eccentricities greater than 1, meaning their paths are hyperbolic. They're moving so fast that the sun's gravity can't capture them. They swing by, get a gravitational nudge, and continue their journey into the cosmic void. 3I Atlas has an orbital eccentricity significantly greater than 1, confirming beyond doubt that it came from interstellar space and will return to interstellar space. It's not ours. It never was. We're just lucky enough to observe it during its brief passage through our cosmic neighborhood. The historic context. Oumuamua and Borisov. To truly appreciate 3I Atlas, we need to understand the 2 interstellar visitors that came before it. 1I Oumuamua was discovered in October 2017, and it absolutely shook the astronomical community. This cigar-shaped object was the first confirmed interstellar visitor ever detected. What made it so bizarre was its unusual acceleration as it left the solar system, a slight but measurable change in velocity that couldn't be explained by the sun's gravity alone. This anomalous acceleration sparked intense debate. Was it outgassing, releasing gas like a comet? Was it being pushed by solar radiation pressure? Or, and here's where things got wild, could it be artificial? Harvard astronomer Avi Loeb famously suggested that Oumuamua might be an alien light sail, a hypothesis that generated massive controversy in the scientific community. The truth is, we don't know what Oumuamua was. We detected it too late, and by the time we realized its significance, it was already leaving the solar system. We never got close-up observations. We never detected outgassing. We never saw a coma, the fuzzy atmosphere around comets. It remains one of the greatest mysteries in modern astronomy. Then came 2I Borisov in August 2019. This interstellar visitor was completely different. It looked and behaved like a comet. It had a coma. It had a tail. It was releasing gas and dust as it approached the sun. In many ways, Borisov was comforting to astronomers because it behaved exactly as they expected an interstellar comet to behave. But Borisov taught us something crucial. Interstellar objects are diverse. Just like objects in our solar system range from rocky asteroids to icy comets to metallic cores, interstellar visitors come in many varieties. Each one is a sample of a different alien solar system, a piece of cosmic real estate from a world we'll likely never see. And now we have 3I Atlas, discovered on July 1st, 2025 by the ATLAS, Asteroid Terrestrial Impact Last Alert System telescope in Chile. And this one is special. What we actually know about 3I Atlas. Let me be crystal clear about what astronomers have actually observed about 3I Atlas, because separating fact from speculation is crucial. Confirmed scientific observations. Hyperbolic trajectory. 3I Atlas has an orbital eccentricity greater than 1, confirming its interstellar origin. It entered our solar system from outside and will leave our solar system never to return. Discovery date, July 1st, 2025, by the ATLAS survey in Chile, a system specifically designed to detect near-Earth asteroids and comets. Designation, C2025N1 Atlas, where SAO indicates it's a long-period comet. 2025N1 indicates it was the first comet discovered in the second half of July 2025, and ATLAS credits the discovering survey. Observable characteristics. As an interstellar comet, it likely exhibits cometary activity, including outgassing, releasing gas and dust as it approaches the Sun, though detailed spectroscopic analysis is ongoing. Origin direction. Based on its trajectory, astronomers can calculate which direction in the galaxy it came from, potentially narrowing down which stellar neighborhood it originated from, though pinpointing a specific star is extremely difficult. What we're still learning. Scientists are currently studying 3I Atlas to determine its exact size and mass, its composition, what elements, molecules, and compounds it contains, its rotation rate and orientation, the chemical signature of its outgassing, if any, how it compares to comets born in our solar system, any unusual characteristics that might distinguish it from solar system comets. This is real science in action. Observations are being made right now, data is being analyzed, and our understanding of this object is evolving daily. Why interstellar objects matter. The Cosmic Sampling Mission. Here's why interstellar objects are so scientifically valuable. They're free samples of other solar systems. Think about it. Our closest neighboring star, Proxima Centauri, is 4.24 light-years away. With our current technology, it would take tens of thousands of years to send a spacecraft there. We can observe exoplanets around distant stars, but we're limited to analyzing their atmospheres from light-years away. We can't touch them, can't sample them, can't study their geology or chemistry up close. But interstellar objects come to us. They're pieces of alien solar systems that travel across the interstellar void and pass right through our neighborhood, close enough for us to observe with our best telescopes and instruments. Every interstellar object tells us something about planetary formation. Elsewhere, the composition of interstellar comets reveals what materials were present in their home solar systems. Different star types create different ratios of elements. By studying these cosmic wanderers, we can learn about planet formation around different types of stars. Ejection mechanisms. How do objects get kicked out of their home systems? Gravitational interactions with giant planets, close encounters with passing stars, supernova explosions. Each interstellar visitor provides clues about the violent dynamics of planetary system evolution. Interstellar chemistry. Space isn't empty. The regions between stars contain gas, dust, and complex molecules. Objects traveling through interstellar space for millions of years get bombarded by cosmic rays and interact with this interstellar medium. Studying their surfaces tells us about the chemistry of deep space. Frequency of ejection. By counting how many interstellar objects pass through our solar system, we can estimate how common this process is. This tells us about the prevalence of planetary systems and the chaos of their formation and evolution. 3I Atlas is our third data point in this cosmic sampling program. Every new interstellar visitor refines our understanding of the galaxy we live in. The Atlas Survey, our cosmic sentinel. The discovery of 3I Atlas wasn't luck. It was the result of a sophisticated early warning system designed to protect Earth from asteroid impacts. The Asteroid Terrestrial Impact Last Alert System, ATLAS, consists of 4 telescopes stationed around the world, 2 in Hawaii, 1 in Chile, and 1 in South Africa. These robotic telescopes automatically scan the entire visible sky every night, looking for anything that moves against the background of stars. Atlas was built primarily to detect potentially hazardous asteroids, space rocks that could collide with Earth. It can detect a small asteroid weeks before impact, or a civilization-ending asteroid months in advance. But it's also become our best tool for discovering interstellar visitors. Here's why. Atlas looks at huge swathes of sky repeatedly, comparing images to detect moving objects. Most objects it finds are asteroids or comets orbiting the sun, but occasionally it spots something moving unusually fast or in an unexpected direction. When that happens, follow-up observations begin immediately to determine if the object is something truly special, an interstellar visitor. The fact that Atlas discovered 3I Atlas tells us something important. We're getting better at detecting these cosmic wanderers. Before 2017, we had never confirmed a single interstellar object. Now we've found 3 in 8 years. This dramatic increase isn't because more interstellar objects are suddenly entering our solar system. It's because our detection capabilities have massively improved. Which raises a mind-blowing question. How many interstellar visitors passed through our solar system before we had the technology to detect them? How many did we miss? And how many are passing through right now, too small or too dark for even our best systems to spot? Now that we've covered the confirmed facts, let's explore the legitimate scientific mysteries surrounding interstellar objects. Questions that real astronomers are actively researching, puzzles that keep them up at night. Mystery number 1. The Oumuamua Acceleration Anomaly. Remember Oumuamua? The first interstellar visitor that accelerated unexpectedly as it left our solar system? This acceleration has never been satisfactorily explained, and it remains one of the most hotly debated topics in astronomy. The acceleration was small but measurable, about 0.0001 times Earth's gravity. That might not sound like much, but it was enough to significantly alter Oumuamua's trajectory over time. And here's the problem. We don't know what caused it. Possible explanations. Outgassing. The comet hypothesis. When comets approach the sun, their ices sublimate, turn directly from solid to gas, creating jets of gas that can push the comet like tiny rocket engines. This is the most conventional explanation for Oumuamua's acceleration. Problem: we never detected any outgassing. No coma, no tail, no spectroscopic signature of gas release. If Oumuamua was outgassing, it was doing so in a completely unusual way, perhaps through vents that were only active on the side we couldn't observe. Solar radiation pressure. Light from the sun exerts pressure on objects. If Oumuamua was unusually flat and thin, like a pancake or a sail, solar radiation pressure could have accelerated it. Problem: for this to work, Oumuamua would need to be about 10 times less dense than any known asteroid or comet. It would essentially need to be an incredibly thin shell, which raises questions about how such a fragile structure could survive millions of years traveling through space. Hydrogen iceberg. Hypothesis. Some scientists proposed that Oumuamua could be made of frozen hydrogen. As it approached the sun, the hydrogen would sublimate but would be invisible to our telescopes. Hydrogen is very hard to detect in space. Problem: Hydrogen ice is so fragile that it's unclear if it could survive the journey through interstellar space without evaporating from cosmic ray impacts. The artificial object. Hypothesis. Harvard astronomer A.V. Loeb famously suggested that Oumuamua could be artificial, perhaps a light sail created by an alien civilization. Problem: there's no evidence of artificial origin beyond the unexplained acceleration. No radio signals, no unusual spectral features, no geometric precision that would indicate engineering. The truth, we still don't know. And that uncertainty is what makes Oumuamua so fascinating and frustrating. Mystery number 2, where do they come from? When we detect an interstellar object, we can calculate its trajectory backward to determine which direction it came from. But direction is complicated in a galaxy where everything is moving. Our Sun orbits the center of the Milky Way at about 514,000 miles per hour. Other stars have their own orbital velocities. By the time an object has traveled for millions of years through interstellar space, tracing it back to a specific star of origin becomes extraordinarily difficult. Think of it like this. Imagine trying to determine where a leaf in a river came from by watching which direction the current carried it. But the river itself is moving. The water is swirling in complex patterns, and the leaf has been floating for years. That's the challenge astronomers face. For Oumuamua, astronomers determined it came from the general direction of the star Vega. But Vega wasn't in that position when Oumuamua would have been ejected from a planetary system. The star has moved. So did Oumuamua come from Vega's system millions of years ago? Or did it come from some other star that happened to be near Vega's current position when Oumuamua was young? We don't know. 2I Borisov came from a different direction entirely, suggesting, as expected, that interstellar objects originate from all over the galaxy. But pinpointing specific source stars remains nearly impossible with current data. 3I Atlas adds another data point. Where did it come from? Which alien sun once illuminated this cosmic wanderer? Scientists are working on the calculations now, but the answer will likely be somewhere in that general region of the galaxy. A volume containing thousands of stars. Mystery number 3. How common are interstellar objects? Here's a question with profound implications. How many interstellar objects are passing through our solar system right now? Based on the detection rate from surveys like Atlas and PANSSTARRS, and accounting for their limited sensitivity, astronomers estimate that at any given moment, there could be 10,000 to 100,000 interstellar objects within Neptune's orbit. Let that sink in. 10,000 to 100,000 objects from other star systems silently passing through our solar neighborhood, and we can only detect a tiny fraction of them. Why so many? Because of the mathematics of planetary system formation. When planets are forming around young stars, the process is chaotic. Gravitational interactions between forming planets, between planets and the remaining debris disk, and between the young planetary system and passing stars can eject countless objects into interstellar space. Current models suggest that for every star in the galaxy, thousands or even millions of objects were ejected during planetary formation. The Milky Way contains about 100 billion stars. Do the math. The space between stars is filled with an unimaginable number of wandering asteroids, comets, and planetesimals. But most are small, less than 100 meters across. They're dark. They're moving fast. We simply don't have the technology to detect them all. We only spot the larger ones, or the ones that happen to pass close to Earth, or the ones that begin outgassing and create a visible coma as they approach the Sun, which means our solar system is constantly being visited by pieces of alien worlds, and we're mostly unaware of it. It's like living in a house where thousands of particles of dust blow in through the windows every day, but you can only see a few of the largest grains. Mystery number 4. The composition puzzle. Every interstellar object we've studied has surprised us with its composition. Oumuamua appeared to be rocky or possibly metallic, unusual for an object originating from the outer regions of a planetary system where ices dominate. Was it a fragment of a rocky planet, a metallic core exposed by a collision? We couldn't tell because we couldn't get spectroscopic data detailed enough to determine its composition. 2I Borisov, on the other hand, had a composition similar to comets in our solar system, but with some intriguing differences. Its gas-to-dust ratio was higher than most solar system comets. It contained significantly more carbon monoxide than expected. These chemical differences tell us that the planetary system it came from had different conditions during formation, perhaps a different temperature distribution, or a different mix of starting materials. Now we're studying 3I Atlas. What will its composition tell us? Will it be similar to our comets, or will it reveal exotic chemistry from an alien stellar neighborhood? Every interstellar object is a mystery box. We don't know what's inside until we open it with our telescopes and spectrographs, and each one teaches us that the galaxy is more chemically diverse than we imagined. Mystery number 5. Are any interstellar objects artificial? Let me be clear. There is currently no confirmed evidence of any artificial interstellar object. None. 0. But here's why this question keeps coming up. The Oumuamua anomaly. When you have an object that accelerates in an unexplained way, and when conventional explanations, outgassing solar radiation pressure, require unusual conditions or properties, it's scientifically reasonable to consider all possibilities, including artificial origin. This doesn't mean Oumuamua was aliens. It means that in the absence of a definitive natural explanation, scientists have a responsibility to consider unlikely but possible alternatives. That's how science works. You examine all hypotheses, including the uncomfortable ones, and you test them against the evidence. Avi Loeb's suggestion that Oumuamua might be an alien light sail was controversial precisely because it was unfalsifiable with our current data. We couldn't prove it wasn't artificial, but we also had no evidence that it was. It's like finding a strange rock and asking, could this have been carved by intelligence? Without clear signs of tool marks or design, you can't tell. The broader point is this. If advanced civilizations exist in our galaxy and have been around for millions or billions of years longer than us, they've likely created artifacts. Some of those artifacts might be wandering through space. The probability that we'd encounter one is extraordinarily low, but it's not 0. So when astronomers encounter something truly anomalous, something that defies conventional explanation, they ask the question, could this be artificial? Not because they expect the answer to be yes, but because failing to ask would be scientifically negligent. With 3i Atlas, scientists will be looking carefully for any signs of unusual behavior, geometric precision, or characteristics that can't be explained by natural processes. They almost certainly won't find any. The universe is strange enough without needing aliens to explain it. But they'll look, because that's what good science demands. Now we're going to shift gears. Everything I've told you so far is based on confirmed observations and mainstream scientific research. But science also thrives on imagination, on asking what-if questions that push our thinking beyond the comfortable boundaries of the known. What follows are speculative scenarios, thought experiments that are scientifically possible, but currently unproven. Think of this as informed science fiction, grounded in real physics and astronomy, but venturing into territory where we don't yet have answers. I'll be clear about what's speculation and what's fact. Let's explore some mind-bending possibilities. What if interstellar objects are panspermia vectors? The science. Panspermia is the hypothesis that life can be distributed across space via asteroids, comets, and other objects. It's a legitimate scientific concept that's been studied for over a century. Here's what we know is true. Microorganisms can survive in space. Experiments on the International Space Station have shown that bacteria can endure years of exposure to the vacuum of space, cosmic radiation, and extreme temperatures when protected inside rocks. Impacts can eject material from planets into space. The asteroid impact that killed the dinosaurs blasted thousands of tons of Earth rock into space. Some of that material escaped Earth's gravity and is now wandering through the solar system or beyond. We've found meteorites on Earth that originated from Mars. This proves that material can travel between planets and survive the journey. The speculation: could interstellar objects carry life between star systems? If microorganisms can survive in space for years, could they survive for millions of years? Could bacteria or hardy extremophiles endure the journey between stars, protected inside rocks or buried in the icy interior of a comet? If so, then interstellar objects like 3i Atlas could be biological delivery systems, not intentionally designed by aliens, but naturally occurring vectors for life distribution across the galaxy. Imagine a comet forms in a planetary system that has a world with life. That world is hit by a massive asteroid. Debris is launched into space, some of it containing microorganisms. This debris gets ejected from the system by gravitational interactions. It wanders through interstellar space for millions of years. Eventually, it enters another star system and crashes into a young planet, seeding that planet with the chemistry or even the biology to kickstart life. This would mean that life in the galaxy could have common origins. Earth life and alien life on distant worlds could be cousins, separated by vast gulfs of space and time, but ultimately descended from the same primordial organisms that hitched rides on cosmic wanderers. How could we test this? If we could send a spacecraft to intercept an interstellar object, collect samples, and return them to Earth, we could search for biosignatures, organic molecules, amino acids, or even preserved microorganisms. We have the technology to do this. NASA's OSIRIS-REx mission successfully returned samples from asteroid Bennu, but intercepting a fast-moving interstellar object would require significantly more advanced propulsion systems and perfect timing. The implications. If panspermia via interstellar objects is real, it would revolutionize our understanding of life's origins and distribution. It would mean that life in the galaxy could be common, seeded across thousands of worlds by natural cosmic processes. It would also mean that when we eventually detect alien life, we might discover it's biochemically related to us, a cosmic family tree written in DNA. What if interstellar objects are deliberately sent? The science. The physics of launching objects between stars is well understood. With enough energy, you can accelerate an object to interstellar velocities. Advanced civilizations might have the technology to do this intentionally. The speculation. What if some interstellar objects aren't natural escapees from chaotic planetary systems, but deliberate launches by alien civilizations? Why would an advanced civilization send objects into interstellar space? Scientific probes. Just as we've sent Voyager 1 and Voyager 2 beyond our solar system as emissaries carrying information about humanity, an alien civilization might launch probes designed to study other star systems. These probes could be smart enough to alter their trajectories, which would explain the Oumuamua acceleration, collect data, and transmit findings back to their creators. Von Neumann probes. In theory, a civilization could build self-replicating spacecraft that explore the galaxy. These probes would arrive at a star system, use local resources to build copies of themselves, and send those copies to other star systems. Over millions of years, a single civilization could explore the entire galaxy this way. Directed panspermia. An advanced civilization wanting to spread life throughout the galaxy might deliberately seed other star systems with microorganisms or prebiotic chemistry. They could launch millions of simple, hardy capsules designed to survive interstellar travel and deliver their biological payloads to promising worlds. Cosmic archaeology. Dead civilizations might have left artifacts scattered through space. Derelict spacecraft, abandoned stations, or automated systems still running long after their creators vanished. These technological fossils would be wandering the galaxy, and occasionally one might pass through our solar system. How could we detect this? If an interstellar object were artificial or deliberately sent, we'd expect to see unusual geometric shapes, spheres, cylinders, or other designed forms. Precise control over trajectory or orientation, emissions of electromagnetic radiation, radio signals, optical beacons. Composition, inconsistent with natural objects, pure metals, exotic alloys, manufactured materials. Internal structure visible through radar imaging. So far, we've detected none of these signs in any interstellar visitor. But the absence of evidence isn't evidence of absence. We simply haven't had the observational capabilities to definitively rule out artificiality. The implications. If even one interstellar object turned out to be artificial, it would confirm we're not alone in the universe. It would prove that technological civilizations exist, or existed, and have mastered interstellar engineering. It would transform humanity's understanding of our cosmic context and potentially provide insights into technologies far beyond our current capabilities. What if 3i Atlas contains unusual chemistry? The science. Every star system forms with a unique chemical composition depending on the elements present in the molecular cloud that collapsed to form the star. Stars born in different regions of the galaxy at different times in galactic history incorporate different ratios of elements. Our Sun is a third-generation star, meaning it formed from material that had been cycled through 2 previous generations of stars. It's made from the ashes of ancient supernovae, which created heavy elements and scattered them through space. But stars in other parts of the galaxy have different histories. Stars born closer to the galactic center might be metal-rich. In astronomical terms, any element heavier than helium is a metal. Stars in the galactic halo might be metal-poor, composed mostly of hydrogen and helium with very few heavy elements. The speculation. What if 3i Atlas came from a star system with radically different chemistry than ours? Imagine a comet formed around a star that has twice the carbon content of our Sun. That comet might contain organic molecules we've never seen, complex carbon chains, unusual amino acids, exotic hydrocarbons that don't exist anywhere in our solar system. Or imagine the opposite, a comet from a metal-poor system composed almost entirely of water ice, methane, and ammonia, with virtually no rock or metal content. It would be a pristine sample of primitive solar system material, less evolved than even the most ancient comets in our solar system. Or consider this, a comet from a system around a binary star where ultraviolet radiation levels were much higher during formation. This might create radiation-processed chemistry that's completely foreign to us, molecules altered by intense UV exposure that we've never encountered. How could we detect this? Spectroscopy, analyzing the light reflected or emitted by an object, can reveal its chemical composition. When 3i Atlas approaches the Sun and begins outgassing, astronomers can use spectrographs to identify what gases it's releasing. They can compare these to the gases released by solar system comets and look for differences. Already, 2i Borisov showed chemical differences from solar system comets, particularly in its CO-H2O ratio. Every interstellar visitor will likely show similar peculiarities, each one a chemical fingerprint of its alien home. The implications. Discovering exotic chemistry in interstellar objects would teach us about the diversity of planetary formation conditions across the galaxy. It would reveal which chemical pathways are universal and which are dependent on local stellar conditions. It might even help us identify which types of star systems are most likely to produce life-bearing planets based on their chemical inventories. What if interstellar objects are more common than we think? The science. Current estimates suggest 10,000 to 100,000 interstellar objects within Neptune's orbit at any given time. But these are estimates based on detection rates and assumptions about the size distribution of interstellar objects. The speculation. What if these estimates are dramatically wrong and the true number is much higher? Consider, we can only detect interstellar objects larger than about 100 meters that pass relatively close to Earth or the Sun. Objects smaller than this are essentially invisible to our current detection systems. But smaller objects would be far more common than large ones. This is true for asteroids in our own solar system. There are millions of small ones for every large one. If the same size distribution applies to interstellar objects, there could be millions or even billions of small interstellar objects, pebble-sized to basketball-sized, within our solar system at any moment. We're swimming in debris from other star systems. Every day, countless tiny fragments from alien worlds might be entering Earth's atmosphere and burning up as meteors. We wouldn't know the difference. We'd assume they're regular meteorites from our own solar system. How could we test this? Advanced meteor detection networks could analyze meteor compositions and trajectories in detail. If we found meteors with unusual chemistry traveling at unusually high velocities, they might be interstellar origin. Space-based meteor detection systems would be even better. They could track objects before they hit the atmosphere. Additionally, sample return missions to collect dust in space could potentially capture interstellar particles. NASA's Genesis mission collected solar wind particles. A similar mission specifically designed to capture high-velocity dust could potentially collect interstellar material. The implications. If interstellar material is constantly raining down on Earth, it would mean our planet is being continuously fertilized with chemistry from other star systems. Every handful of dirt might contain atoms that originated in alien worlds. The boundary between Earth material and space material becomes blurred. We're all made partly of stardust from distant suns. What if we could visit an interstellar object? The science. Sending a spacecraft to intercept an interstellar object is theoretically possible, but extremely challenging. The problem is speed and notice. Interstellar objects are moving fast, typically 20 to 40 kilometers per second relative to the Sun. To intercept one, a spacecraft would need to match that velocity, which requires enormous amounts of energy. Additionally, we usually discover interstellar objects when they're already close to the Sun, giving us very little lag time. By the time we confirm an object is interstellar, organize a mission, build and launch a spacecraft, it's often already leaving the solar system. But with enough warning, it's possible. The speculation. Imagine if Atlas detected an interstellar object while it was still beyond Jupiter's orbit, months or even a year before its closest approach to the Sun. That would give us time to launch a fast response mission. The spacecraft wouldn't need to rendezvous, match velocities with the object. Even a high-speed flyby lasting just minutes could capture incredible data. High-resolution images of the surface, spectroscopic analysis of composition, measurements of mass and density, and potentially even samples of gas and dust for analysis. NASA has already designed concept missions for this purpose. The bridge concept would use a spacecraft kept in constant readiness, fueled and equipped, waiting in orbit for an interstellar visitor to be detected. When one is spotted, the spacecraft would launch immediately, using a gravity assist from Jupiter to boost its velocity and intercept the target. Such a mission could transform our understanding of interstellar objects. Instead of observing them from hundreds of millions of kilometers away, we could see their surfaces up close, analyze their structure, and directly measure properties we can currently only infer. The implications. A successful interstellar object intercept mission would be humanity's first direct physical interaction with material from another star system. It would be like shaking hands with an alien world, not life, but the next best thing. The data collected could reveal formation processes around other stars, test our theories of planetary chemistry, and perhaps even detect organic materials or biosignatures from distant worlds. More importantly, it would prove that human technology has advanced to the point where we can actively study interstellar objects, rather than just passively observing them. It would be a major milestone in our journey to becoming an interstellar species ourselves. Now let's zoom out and look at the bigger picture. What do interstellar objects, 3I Atlas, Borisov, Oumuamua, and the thousands we haven't yet detected, tell us about the universe we live in? The galaxy is interconnected. The existence of interstellar objects proves that the galaxy is not a collection of isolated star systems, but an interconnected network. Material flows between stars. Objects ejected from one system can enter another. What happens in one corner of the galaxy can, over millions of years, affect what happens in another corner. This has profound implications. It means stellar evolution is shared. When a massive star explodes as a supernova, it doesn't just enrich its local neighborhood with heavy elements. It blasts material across light years of space. Some of that material ends up in other star systems, seeding them with the chemical building blocks for planets and potentially life. The iron in your blood came from a supernova that exploded billions of years ago, but not necessarily in our solar system's immediate vicinity. It could have traveled from a distant stellar explosion. Chemical exchange. Interstellar objects carry chemistry from one star system to another. This means that the chemical inventory of star systems isn't solely determined by local conditions. It's also influenced by material imported from elsewhere. Over billions of years, this exchange could homogenize the chemistry of neighboring star systems to some degree. Biological exchange, maybe. If panspermia is real, then the galaxy isn't just chemically interconnected, it's biologically interconnected. Life could have multiple origins and multiple distribution routes. Earth life, if it originated here, might still have been influenced by organic chemistry delivered from other systems. Or Earth life might have originated elsewhere entirely and been delivered here by an ancient interstellar comet. This interconnectedness changes how we think about ourselves. We're not just citizens of Earth, or even just citizens of the solar system. We're citizens of the Milky Way, participants in a grand cosmic exchange that's been happening since the first stars formed. Planetary systems are violent. The existence of so many interstellar objects tells us something important. Planetary system formation is a violent, chaotic process. In our own solar system, we see evidence of this ancient chaos. The late heavy bombardment about 3.9 billion years ago saw countless asteroids and comets crash into the inner planets. Uranus is tilted on its side, likely from a massive collision. Neptune probably migrated outward, scattering objects throughout the outer solar system and creating the Kuiper Belt. But most of the violence happened earlier, during the first few 100 million years when planets were still forming. During this period, countless objects were ejected from our solar system entirely, sent on one-way trips into interstellar space. Every star with planets probably went through similar chaos, which means the space between stars is filled with the debris of planetary system formation, the leftovers, the objects that didn't make the cut, the wanderers that lost their homes. This violence isn't a bug, it's a feature. It's how planetary systems clean themselves up, removing excess material and settling into stable configurations. But it also means that for every stable solar system we observe today, countless objects were sacrificed, sent into the cosmic wilderness to wander forever. We're not special. One of the most humbling lessons from interstellar objects is this: our solar system isn't unique. When we study 2I Borisov, we find it's chemically similar to our comets. When we detect interstellar objects passing through regularly, we realize this is a normal cosmic process. Our solar system formed from the same types of materials, through the same types of processes, as countless other systems throughout the galaxy. This has implications for the search for life. If our solar system is typical, then the chemistry that led to life on Earth probably exists in many other systems. The conditions that allowed Earth to remain habitable, liquid water, protective atmosphere, magnetic field, probably occur around many other stars. The processes that led from chemistry to biology on Earth could have occurred elsewhere. We're not cosmically special. We're an example of what happens naturally when physics, chemistry, and time come together in a planetary system around a middle-aged yellow star. This is simultaneously humbling and exciting. Humbling because it removes us from any cosmic pedestal. We're not the center of anything, not unique, not specially placed. But exciting because it means whatever happened here probably happened elsewhere too. Life, intelligence, civilization. If they emerged on Earth, they probably emerged elsewhere as well. The universe operates on timescales we barely comprehend. Interstellar objects force us to think in millions of years. 3I Atlas has been traveling through space for an incomprehensibly long time. It was ejected from its home system when, millions of years ago, tens of millions, we don't know. But during that journey, on Earth, entire species evolved and went extinct. Continents drifted across the globe. Ice ages came and went. Human civilization rose from nothing. And throughout all of that, 3I Atlas was traveling silently through the void, passing other star systems perhaps, navigating the gravitational currents of the galaxy, making its way toward a small, unremarkable yellow star it would visit for just a few months before continuing its eternal journey. This is the time scale of the cosmos. Interstellar objects are time travelers, not in the science fiction sense, but in the real sense. They carry information from one epoch to another, from one stellar neighborhood to another, on journeys that dwarf human history. It's sobering. It reminds us how brief our existence is on cosmic scales, but it's also inspiring. These objects prove that even on cosmic timescales, things happen. Motion, change, events. The universe isn't static. It's dynamic, evolving, full of processes that play out over millions of years, but are nonetheless real. The future of interstellar object research. Where do we go from here? How will our study of interstellar objects evolve in the coming years and decades? Better detection. New survey telescopes are coming online that will dramatically increase our detection rate. The Vera Rubin Observatory, scheduled to begin operations soon, will survey the entire visible sky every few nights. It will detect interstellar objects earlier, while they're still farther from the Sun, giving us more time to study them, or even launch missions to intercept them. Rapid response. Missions. Space agencies are seriously considering maintaining spacecraft in readiness for rapid deployment when interstellar objects are detected. These fast response missions would be pre-built, pre-fueled, and waiting in orbit. When a suitable target is identified, they'd launch within days or weeks, using gravity assists and high-efficiency propulsion to intercept the object. Advanced spectroscopy, next-generation telescopes like the James Webb Space Telescope and ground-based, extremely large telescopes will provide unprecedented spectroscopic capabilities. They'll be able to analyze the composition of interstellar objects in exquisite detail, identifying specific molecules, isotope ratios, and chemical signatures that tell us about their origins. Sample return. The Holy Grail would be capturing actual physical samples from an interstellar object and returning them to Earth for laboratory analysis. This is technologically challenging, but not impossible. The scientific payoff would be enormous. We could study alien solar system material with the full power of Earth-based laboratories. Statistical analysis. As we detect more interstellar objects, we'll be able to perform statistical analyses. How common are different types? Rocky, icy, metallic. What's the size distribution? Do certain trajectories or compositions correlate? This statistical approach will reveal patterns that individual objects can't show us. The field of interstellar object research is just beginning. We're at the stage where every new detection is a major event, every observation generates surprises, and every analysis raises new questions. In a decade, we might have detected dozens of interstellar visitors. In a century, interstellar object studies might be a mature scientific discipline with textbooks, established theories, and regular observations. Let's go even deeper. Beyond the science, beyond the speculation, what do interstellar objects mean for humanity's place in the cosmos? We are surrounded by alien worlds. Every interstellar object is a physical piece of an alien world. Not alien life, probably, but alien geology, alien chemistry, alien planetary processes. When you look at images of Oumuamua or Two-Eye Borisov or Three-Eye Atlas, you're looking at matter that formed around another star. Atoms that were heated by a different sun, shaped by different gravitational forces, carved by different impacts and processes than anything in our solar system has experienced. This is as close as we currently get to touching an alien world. And it's happening regularly. Right now, somewhere beyond Jupiter, invisible to our telescopes, objects from distant star systems are silently passing through our solar system. We are literally surrounded by samples of alien worlds. We just can't see most of them. This should fundamentally change how we think about our cosmic environment. Space isn't empty. The solar system isn't isolated. We're constantly being visited by messengers from distant suns, and we're only just beginning to notice. The cosmic perspective. Interstellar objects force what Carl Sagan called the cosmic perspective, the ability to see ourselves from outside our own limited viewpoint. Think about it. Three-Eye Atlas doesn't care about human politics, economics, religions, or conflicts. It doesn't care about stock markets or elections or who said what on social media. It's a 4-billion-year-old piece of cosmic ice that's been traveling through the galaxy for longer than human civilization has existed. and it's just passing through our neighborhood on its way to somewhere else. From the perspective of 3i Atlas, Earth is just another planet orbiting just another star. We're not special to the universe. We're participants in cosmic processes that were happening billions of years before we existed, and will continue billions of years after we're gone. This perspective is simultaneously humbling and liberating. Humbling because it removes any illusion of cosmic importance, but liberating because it frees us from the narcissism of thinking the universe was made for us or revolves around us. We're part of something vast, ancient, and ongoing. Interstellar objects are reminders of that vast cosmic context. The possibility of contact. Here's a thought that keeps astronomers up at night. What if we've already been visited by artificial objects and didn't recognize them? Not Oumuamua specifically. There's no good evidence it was artificial. But consider, if advanced civilizations exist and have been around for millions or billions of years, they've likely created artifacts that have been wandering the galaxy for a very long time. Some of those artifacts might have passed through our solar system before we had telescopes. Some might have passed through while we had telescopes, but were too small or too dark to detect. Some might be in our solar system right now, inactive and silent, waiting for something. This isn't conspiracy theory territory. It's a legitimate scientific possibility that's worth considering. The universe is 13.8 billion years old. Humans have had the technology to detect interstellar objects for about 10 years. The probability that we'd encounter an artificial object during our brief observational window is low, but it's not zero. And here's the thing. If an advanced civilization wanted to study emerging technological species, like us, one efficient method would be to send small monitoring probes to lots of star systems. These probes would be small, dark, inactive most of the time, and nearly impossible to distinguish from natural asteroids, unless you looked very carefully. They'd be the galaxy's surveillance network, patiently watching, recording, waiting for signs of intelligence on the worlds they orbit. Science fiction? Maybe, but the physics allows it. The economics of it, for a sufficiently advanced civilization, might make sense. And our current detection capabilities wouldn't rule it out. So when astronomers carefully analyze each new interstellar object, looking for any signs of artificial origin, they're not being crazy. They're being thorough. Because the day we definitively identify an artificial object, a probe, a derelict spacecraft, any clear sign of technology would be the most significant day in human history. It would mean we're not alone. It would mean intelligence is or was out there. And it would mean the universe is far stranger and more populated than we currently believe. The question of uniqueness. Interstellar objects also force us to confront a deep philosophical question. How unique is Earth? Every interstellar visitor adds data to this question. Each one tells us about planetary chemistry elsewhere, about the processes that shape worlds around other stars, about the materials available for planet formation throughout the galaxy. So far, what we've learned is this. The chemistry isn't wildly different. 2I Borisov contained water, carbon monoxide, and dust, similar to our comets, though with different ratios. The physics is the same. Gravity works the same way everywhere. Ices sublime the same way, orbital mechanics follow the same rules. This suggests that the processes that formed Earth and led to life on Earth are probably common. The building blocks are everywhere. The physical laws are universal. If you put the pieces together in the right environment, you get planets. And on some of those planets, you get life. Earth might not be unique. Life might not be unique. Intelligence might not be unique. But here's the paradox. If life and intelligence are common, where is everyone? Why haven't we detected any signs of advanced civilizations? Why do interstellar objects appear to be natural rather than artificial? This is the famous Fermi paradox, and interstellar objects are relevant to it. Every natural interstellar object we detect, every one that's clearly just a rock or a comet, is data suggesting that at least in our local galactic neighborhood, technological civilizations aren't common enough to fill space with artificial objects. Maybe we're earlier than most. Maybe intelligence is common, but long-lasting technological civilizations are rare. They destroy themselves, or transcend physical form, or lose interest in space. Maybe the galaxy is vast enough that even numerous civilizations are thinly spread and unlikely to overlap. Or maybe, and this is the possibility that keeps me up at night, maybe we're the first. Maybe in our corner of the galaxy, at this particular moment in cosmic history, we're the first species to ask these questions, to build telescopes, to detect interstellar visitors and wonder about their origins. If that's true, we carry an enormous responsibility. We're not just a species, we're potentially the galaxy's first conscious witness to itself, the first intelligence to wake up and look outward. That's both terrifying and exhilarating. So where does the story of Three-Eye Atlas go from here? What can we expect in the coming months and years? Immediate observations. Right now, astronomers around the world are pointing every available instrument at Three-Eye Atlas. They're collecting data on trajectory refinement, calculating its exact path through the solar system, determining precisely where it came from and where it's going. Composition analysis. Using spectroscopy to identify what chemicals and molecules it contains. As it approaches the Sun, if it hasn't already passed perihelion, closest approach, it will heat up and release gases that can be analyzed. Physical properties, estimating its size, shape, rotation rate, and mass. These properties tell us about its structure and formation history. Activity patterns, monitoring for outgassing, tail formation, fragmentation, or any unusual behavior. Does it behave like our comets, or does it show unexpected characteristics? Comparison with predecessors. How does it compare to Oumuamua and Two-Eye Borisov? Is it more similar to one than the other? Does it represent a new category of interstellar object? This observational campaign will continue for as long as Three-Eye Atlas remains bright enough to study, probably several months at minimum, possibly longer depending on its size and activity level. Publication and analysis. The initial observations will be published in scientific journals, where they'll undergo peer review by other astronomers. Then the real work begins. Deep analysis of the data, computer modeling of its formation and evolution, comparison with theoretical predictions. This process takes time. The first papers on Oumuamua were published within weeks of its discovery, but we're still publishing new analyses of that object years later. Scientific understanding builds slowly as multiple researchers examine the data from different angles, test different hypotheses, and build on each other's work. With 3i Atlas, we'll likely see initial discovery papers describing its basic properties, spectroscopic analyses revealing its composition, dynamical studies tracing its origin and evolution, comparative studies examining how it differs from solar system comets, theoretical papers proposing formation scenarios for its unusual characteristics, if it has any. Each paper will add another piece to the puzzle, and gradually, a picture will emerge of what 3i Atlas is and where it came from. Future detections. 3i Atlas won't be the last interstellar visitor we detect. Based on current detection rates and improving survey capabilities, we can expect to discover new interstellar objects regularly, perhaps several per year once next-generation surveys come online. Each new detection will add to our statistical understanding. After 10 or 20 interstellar objects, we'll be able to say things like X% of interstellar objects show cometary activity. The typical size range is between Y and Z meters. Objects from this direction tend to have this composition. The galactic ejection rate is approximately N objects per star per million years. This statistical approach will reveal patterns that individual objects can't show us. We'll start to understand interstellar objects as a population rather than as individual anomalies. The search for artificial objects. As our detection capabilities improve, the search for artificial interstellar objects will become more systematic. Several research groups are developing protocols for identifying potential techno-signatures, signs of artificial origin, in astronomical objects. These protocols include geometric analysis, looking for precise geometric shapes, perfect spheres, cylinders, regular polyhedra that would indicate manufacturing rather than natural formation. Trajectory anomalies, monitoring for acceleration or deceleration that can't be explained by natural forces, or for trajectory changes that suggest active maneuvering. Electromagnetic emissions, searching for radio signals, optical beacons, or other electromagnetic emissions that would indicate active technology. Spectroscopic anomalies, looking for spectral signatures of manufactured materials, pure metals, exotic alloys, or synthetic compounds that don't occur naturally. Structural analysis, using radar imaging to look for internal cavities, geometric patterns, or other structures that might indicate artificial construction. So far, no interstellar object has triggered any of these detection criteria. But the search continues because the payoff for a positive detection would be transformative. Mission concepts. Multiple space agencies and private organizations are developing concepts for missions to intercept interstellar objects. These concepts range from small, fast-response probes to ambitious sample return missions. ESA's Comet Interceptor. The European Space Agency is developing a spacecraft called Comet Interceptor, designed to wait at a gravitationally stable point in space until a suitable long-period comet or interstellar object is detected. It would then redirect to intercept the target, performing a high-speed flyby with multiple subspacecraft collecting different types of data. NASA's Bridge concept. NASA has studied a bridge mission that would maintain a spacecraft in readiness, potentially in orbit around Earth, or at a strategic location in the outer solar system. When an interstellar object is detected with sufficient lead time, the spacecraft would launch immediately to intercept it. Private initiatives. Organizations like the Breakthrough Initiatives have expressed interest in funding missions to study interstellar objects. Private funding could enable faster, more flexible mission development than traditional government space programs. The challenge with all these concepts is timing and propulsion. Interstellar objects move fast and give us little warning. Successfully intercepting one requires early detection, while the object is still far from the Sun. Rapid decision-making, mission approval and launch within weeks or months. High-efficiency propulsion to match velocities with a fast-moving target. Advanced autonomy. The spacecraft must navigate and collect data with minimal human input due to communication delays. These are solvable problems, but they require investment, planning, and readiness. The first successful interstellar object intercept mission will be a major milestone in space exploration. The long view. Let's zoom out even further and think about the long-term future of humanity's relationship with interstellar objects. In 10 years, we'll probably have detected dozens of interstellar objects. We'll have a much better statistical understanding of their properties, origins, and diversity. We might have successfully intercepted one with a spacecraft, collecting close-up images and data. The study of interstellar objects will be an established field of astronomy with dedicated researchers and regular conferences. In 50 years, interstellar object detection might be routine. Advanced survey telescopes might detect them regularly, even small ones. We might have returned samples from an interstellar object to Earth for laboratory analysis. We'll understand the galactic context of these objects much better, which types of star systems produce them, how they're distributed through the galaxy, and what they tell us about planetary system evolution. In 100 years, we might be sending our own objects into interstellar space intentionally. Scientific probes designed to study other star systems. We'll have transformed from passive observers of interstellar visitors to active participants in interstellar exchange. The boundary between our solar system and interstellar space will become less meaningful as we routinely track, study, and even interact with objects passing through. In 1,000 years, if humanity becomes an interstellar species, a big if, we'll encounter interstellar objects from the perspective of travelers rather than stationary observers. Our spacecraft crossing between stars will pass numerous wandering asteroids and comets, some from our own solar system, some from systems we're traveling to, and some from entirely different stellar neighborhoods. The galaxy will reveal itself as a complex, interconnected network of stellar systems, exchanging material and perhaps information. This is the future that interstellar objects like 3I Atlas are pointing us toward, a future where humanity thinks and operates on galactic scales, where we're not confined to one star system, where we're participants in the cosmic exchange that's been happening since the galaxy formed. So let's bring this all together. What does 3I Atlas and interstellar objects in general really mean for humanity? At the most basic level, they're scientifically valuable. They're samples of other star systems delivered to us for free. Every one we study teaches us about planetary formation, stellar chemistry, and galactic dynamics. They're natural laboratories for testing our theories about how solar systems form and evolve. But they're more than just scientific curiosities. They're also philosophical provocations. They remind us that we're not alone in the universe, not in the sense of finding alien life, not yet, but in the sense that we're surrounded by material from other worlds, that our solar system is constantly being visited by cosmic wanderers, that the galaxy is interconnected in ways we're only beginning to understand. They challenge us to think bigger, to expand our perspective from Earth to solar system to galaxy, to think in timescales of millions of years, to consider possibilities that seem like science fiction but are actually grounded in real physics. They humble us by showing how brief and small our existence is on cosmic scales, but they also inspire us by proving that even on those vast scales, interesting things happen. Material moves, chemistry evolves, objects travel between stars carrying information about the worlds they came from, and perhaps most importantly, they give us a glimpse of humanity's possible future. If we survive, if we mature as a species, if we develop the technology and wisdom to become an interstellar civilization, we'll join the cosmic exchange that's been happening for billions of years. We'll send our own objects into the galaxy, probes, spacecraft, maybe even self-replicating machines that spread throughout nearby star systems. We'll transform from observers to participants. 3i Atlas is a messenger from that future, showing us what's possible when you think on galactic scales and operate with patience measured in millions of years. So the next time you look up at the night sky, remember, somewhere out there, right now, objects from distant star systems are silently passing through our solar neighborhood. Most are invisible. Most will never be detected. But they're there, cosmic voyagers on journeys that began before human civilization existed and will continue long after we're gone. And occasionally, if we're lucky, if we're watching carefully with our best telescopes and our most sophisticated detection systems, we catch a glimpse of one. We see it for a brief moment against the backdrop of stars. We study it, analyze it, try to understand where it came from and what secrets it carries. Then it's gone, continuing its eternal journey through the galaxy. 3 Atlas. Is that glimpse a visitor from the cosmic wilderness, a sample of an alien world, a reminder that the universe is vast, ancient, interconnected, and full of wonders we're only beginning to discover? The cosmos is calling. Interstellar objects are the messengers, and humanity is finally learning to listen. If this exploration has expanded your cosmic perspective, hit that like button and subscribe for more deep dives into the mysteries of space. Drop a comment below. What do you think about interstellar objects? Do you believe some could be artificial? What would you want to ask an alien civilization if we found evidence of one? Your thoughts contribute to a global conversation about humanity's place in the universe. Let's explore these cosmic mysteries together. And remember, right now, as you're reading this, somewhere beyond Neptune, an object from another star system is silently passing through our solar neighborhood. The galaxy is more connected than we ever imagined. Welcome to the age of interstellar discovery.